colloids have negatively charged surfaces. This means that positive ions, or charged particles in water, will attract to the colloid surface, forming a first layer. Recall how like poles of a magnet will repel, while opposite poles will attract. The same occurs with colloids in water. A diffuse layer, made up of a mix of positive and negative ions, will then surround the first, forming what is called a double layer. This double layer provides a repulsive force that prevents two colloids from sticking to each other. Once the flocculant is added, it adheres to the surfaces of the particles, compressing the double layer and allowing the colloids to stick to each other and form flocks.
We are performing jar tests which simulate the operation of the MBC. The first simulation is on stormwater which contains silt and clay. As a first step, we measure the turbidity of this sample, and it is 369 FAU. The first thing we do is begin mixing of the samples, as is done in the MBC unit. We add magnetite. Magnetite is an inert iron oxide. It's non-reactive, non-toxic, and is found naturally occurring as the black sand seen in many streams throughout the world. We next add a small bit of polymer, and this allows the particles we want to remove to adhere to the magnetite. The magnetite is 5 times the density of water, so once we stop the mixing, particles will settle very rapidly. We only mix for about 30 seconds in this simulation, while in an MBC, the mixing is actually about 5 minutes. This allows for a much better removal sometimes of the very, very fine particles. The sample, when the mixing stops, settles quite rapidly, with most particles removed in less than 30 seconds. The vast majority of particles have already settled out, but magnetite is also magnetic, and so we can remove them magnetically if need to. The final turbidity of this sample was 9 FAU, which represents over 97% removal